We'll come to an example on how to use a divergence theorem to evaluate a flux integral or the surface integral shown here, where the vector field F is given and the surface S is the solid bounded by the cylinder y squared plus c squared equals 25 and the planes x equals -4 and x equals 3. Let's first look at this graphically. The surface S is the surface that bounds the cylinder between these two yellow planes, which are x equals -4 and x equals 3. And the vector field F is graphed in purple, and therefore the value of the flux integral will give us a net flow across the surface of this cylinder. Before we set this up, though, let's review the divergence theorem. The divergence theorem states the total divergence of a vector field in a solid region V equals the total flow across the boundary surface S, where V must be a solid region bounded by S, oriented by a unit normal vector directed outward, and the partial derivatives of the components of the vector field F must be continuous on V. So under these conditions, the flux integral, often expressed in one of these two forms, is equal to the triple integral over the region V of the divergence of the vector field F differential V, which can also be expressed in this form here. So this shows a relationship between a triple integral over a solid region and a surface integral over a surface. So going back to our example, looking at the vector field F and our formula, P equals 3xy squared, Q equals x e to the z, and R equals e to the third. So let's go ahead and find these partial derivatives. So the partial of P with respect to x is equal to the derivative of 3xy squared with respect to x, that'd be 3y squared. And the partial of Q with respect to y is equal to the derivative of x times e to the power of z with respect to y, which would be 0. And the partial of R with respect to z is equal to the derivative of z to the third with respect to z, which would be 3z squared. Which means the given surface integral, or flux integral, again often expressed as the double integral over the surface S of f dot n differential S, is equal to the triple integral over the solid region V of the sum of the partial derivatives, which would be 3y squared plus 3z squared differential V. And now because the surface S is a cylinder, it does make sense to use cylindrical coordinates. But we need to be careful here, though, because notice how the cylinder is running along the x-axis and is bounded by x equals -4 and x equals 3. So differential V is not going to be equal to r dz dr d theta. It's going to be equal to r dx dr d theta. Again, because the cylinder is running along the x-axis, not the z-axis. And that also means y squared plus c squared is equal to r squared. So this triple integral is equal to the triple integral of, well, if we factor out 3, we're going to have 3 times the quantity y squared plus c squared, which would be 3r squared. Then again, differential v is equal to r dx dr d theta. The limits of integration for x are going to be from -4 to 3. We can use the yz trace if we need to help us find the limits of integration for r and theta. The limits of integration for r from 0 to 5, and for theta it's from 0 to 2 pi. Let's go and evaluate this on the next slide. Well, of course, we can write the integrand function here as 3r cubed. So we first integrate with respect to x, treating r as a constant. So we'd have 3r cubed x performing substitution for x. When x is 3, we have 3r cubed times 3 minus, when r is -4, we have 3 times r cubed times -4. So we have 9r cubed plus 12r cubed, which gives us 21r cubed. And now we integrate with respect to r. So the antiderivative is going to be 21 times r to the fourth divided by 4, or 21/4 r to the fourth. Performing substitution for r, when r is 5, we have 21/4 times 5 to the fourth. And when r is 0, we have 0. This simplifies to 13,125 fourths d theta. And now we integrate with respect to theta. Performing substitution for theta, we're just going to have 13,125 divided by 4 times the quantity 2 pi minus 0. Of course, we have a common factor of 2. So 1, 2, and 2, and 2 2s and 4. So the exact value of the flux integral is 13,125 pi divided by 2, which is approximately 20,616.7018. So going back to the graph, this value represents the total flow across the boundary surface S, as well as the total divergence of the vector field in the solid region V. I hope you found this helpful.